Hello, welcome everyone. In this session, we have Chaya Choudhary, Senior Data Scientist at Zscaler, and Laura Rocha, Data Scientist at Infoblox, presenting The Adventures of Reproducibility and Machine Learning, a cybersecurity use case. Just a quick note to the audience to please post your questions to the Q&A box instead of the chat. Chaya, Laura, a reminder to start your timer. Off to you.
Thank you, Jennifer. I'm Chaya Choudhary. I'm a senior data scientist at Zscaler, where I'm working on developing machine learning solutions for Zscaler zero-trust workload segmentation. And prior to that, I worked at Infoblox along with Laura, and where my research focused on using machine learning and deep learning algorithms to solve some of the challenging problems involving malware detection using large amounts of DNS data.
Okay, thank you, Chaya. So my name is Laura Rocha. I am also senior data scientist, currently working for Infoblox. So for the past 3 years and a half, I worked in a variety of projects while I was during my time at the company, and I worked a lot with ranking data. And currently, I try to focus my work on creating solutions for our security product. And I'll be the one to start the presentation today, so I'll just go ahead and start it. So our talk today is about the adventures of reproducibility machine learning. And specifically, we're going to be talking about a cybersecurity use case. And to give you a little bit of a background on how me and Chaya came up with the idea of this talk is, as Chaya mentioned, we have worked together for a long time at Infoblox. So this is where this work took place. And we both joined the company when we were in similar stages of our career in data science. And specifically, I had just graduated from my degree in statistics. Chaya had just obtained her master's in computer science. And often we'd get together and, discuss about our experience in going from this transition from just recently having graduated and working into applied machine learning in the real world. And a common topic that we discussed was around things that they don't tell you in school. So our talk today is intended to give you a little bit more visibility on certain aspects of machine learning in the real world and some of the lessons that we learned along the way. And hopefully we can give you some tips on how to overcome some of these challenges. So as I mentioned, the agenda for this presentation is we want to go over some experiments and some hypotheses that we had when we were trying to reproduce a research paper. And we wanted to talk a little bit about some of the reproducibility issues we encountered, how do you overcome the challenges, and hopefully highlight some key takeaways. So our story starts with a porcupine. So imagine a hypothetical scenario that I was given the task of creating an amazing birthday cake for a party. So I start Googling online, I try looking for recipes, and I stumble into this beautiful cake that I want to try to recreate. So I go to the grocery store, I buy all the ingredients, I go home, I bake it, and I end up like this. Nailed it. If you understand the reference, you understand it, but the idea, it doesn't look quite the same. And there are a few reasons for this. It could be because maybe there's something wrong with the recipe, or we have the wrong ingredients, or it could be an issue with the chef. But once you start understanding which one is the issue, you already have an idea of how to fix the problem. But why am I talking about this? It's because the same occurs in machine learning. So we're often handed a task that we're supposed to solve, and we'll start our process by searching and doing some literature review for problems and solutions and studies that have solved a similar issue than ours. And most of the times when we're trying to recreate some of these existing solutions applied to our own environment, we end up not obtaining the same results. So reproducibility machine learning is first because creating generic classifiers with reproducible results that hold across different data sets is difficult. If this was an easy task to do, for example, for a specific classification problem, we would have a single pickle file for a model that you trained. We would share it with the world, and then everyone that has that particular test can apply it to their own data and that would work just fine. But we know that's not the case. And on the other hand, whenever we're in school or learning the data science and machine learning field, we learn how to split our data into training, validation, and testing. And we use our training and our validation for training our model, for tuning our parameters. And we use this test data that we have not seen and not touched for evaluating the performance of our model. However, once you join the workforce, one thing that whenever you join the workforce, we follow the same process. We use our training, our validation. We look into our test data. Okay, we're content with the performance. Let's deploy it into production. And whenever we circle back and try to review the results of our classifications, we end up observing that the performance doesn't seem quite the same as when we trained our data, when we trained our algorithm. So this is basically what we want to talk in this presentation is some of the reproducibility issues that is seldom discussed when you're learning the field, and some of the tips of how to get over that. And why is reproducibility important? Because whenever we're handed a task, we want to try to take advantage of existing knowledge and studies that have solved a similar problem than ours, so we don't have to start from scratch. And we want to be able to study if certain techniques are applicable to our use case with results that we can leverage. And more than taking advantage of whatever people have already done in the past, is we want to be able to understand if there are other factors that impact the performance of the model that we should take into account when creating it. So I went over a little bit about the background, and what we wanted to do for this talk is to kind of showcase some of these issues. We selected a research paper that we could easily reproduce because they had publicly available data. And our hypothesis is that whenever that the performance of the classifier on a newly unseen set of data, which would kind of be the equivalent to the production data, will be lower than the results reported in the paper. Specifically, we're going to be talking about file classification. In this case, we're trying to distinguish between malicious and legitimate portable executable files. And the methodology here was to use the publicly available data provided for training the algorithm, follow the same procedures that the author of the paper did, do feature extraction. In this case, they do provide code, which was nice. So we partner with our threat researchers to obtain those. Once we trained the model on the data provided, we tested it on a newly collected set of data that we collected from a completely different environment. And we wanted to compare the performance between these two data sets. So the original test data that evaluating the performance when creating the classifier versus what would mimic a production environment or a completely different data set collected from a different environment. So let me make a small pause just to everything to kind of sit in. Okay, so here I'll talk a little bit about the experiment. So here on the left, we basically followed the same procedure. We trained multiple classifiers to try to pick the one that had the best performance. Here on the left, we can observe the AUC there under the curve for 6 different algorithms on the original test data set. We can observe that the area under the curve for random forest seemed to be the best, around 0.99. But from a brief evaluation on applying the 6 algorithms into our newly unseen collected data set, we can see that the performance of the model decays just by eyeballing this graph. We did look into, for picking the model, so we do look into the other metrics, accuracy, precision, recall. It did seem like random forest was the best on the original test data set. So we went ahead and moved with this model for making our comparisons. And in this next slide, we basically summarize what we were trying to say, that creating a generic classifier that holds across data set is difficult. So if we compare these metrics, on the bottom, we have the accuracy of the original test data around 0.98. And in our unseen test data set, we have an accuracy of 0.82. So we can see that has decayed. If we move into the right, we can see that the precision was actually pretty close. So that was a pleasant surprise. So it does mean that in the original test, we had a precision of 0.98. In our case, we had a precision of 97. So this means that this algorithm is able to generalize and classify the positive cases correctly. If we move ahead to recall, we can see that it has decayed from 0.98 to 0.82, which means that it's failing to capture some of the positive cases. And that's probably why the accuracy is low as well. So mainly out here, we can start making a diagnosis of what's happening. So why is recall lower in this case? It's possibly because there is a feature that doesn't hold in our newly collected data set. And one thing important to notice here is that precision here was similar, which is very good, specifically for a cybersecurity use case in which we're really worried about the false positives. So imagine a scenario that one of the algorithms incorrectly detect, let's say GitHub as malicious, and we decide to block it. So that will make a lot of people angry. So false positives is really something that we're worried when we're talking about cybersecurity. So in this case, it's nice that we saw that we had a good performance. But in general, we can see that recall was not good. We didn't obtain the same results. And the question really here is, why is this happening? What are the possible things that cause this to not have similar results or the same results? And Chaya will dive into that.
Thank you, Laura, for going into the details of the experiments and performance results. So let's now dive deep into some of the reproducibility issues we faced while working on this project, as well as some of the issues we observed working in the industry for these years. So at the tip of the iceberg, we see shallow issues like collecting all the features. Many a times we miss small details while extracting the features. For example, after extracting the features for our newly unseen collected dataset from the code which was provided to us, we were to convert some of these features to their Boolean values, and we missed converting 2 of those values. We noticed that later. As Laura also explained, like we had only 69 features. Imagine a scenario where you are given, 200 features, and then you also extract some features, and that increases the dimensionality of your feature set. As a human, we make mistakes, and it is really difficult to manually inspect all these problems. Sometimes it is also not possible to extract the same value for the features. And this is because majority of research in cybersecurity doesn't share any code. So people might have different ways of extracting the same features from a feature definition. So being aware of all these issues while collecting the features is very important. Second thing we want to highlight is sometimes when creating models using default parameters, we don't pay attention to which library version of the classifier is being used, right? Let me give you an example. sklearn version 0.19 for random forest earlier used to have default number of trees as 10. But now, as we have a newer sklearn 0.22 version, the default number of trees have increased to 100. So you now know the difference between, why you are getting different performance. Because earlier you were using 10 trees and now you're using 100 trees. One of the other things to keep in mind is randomness in machine learning, which is often introduced by using random seed. Like we use always different random seeds, and obviously the results are going to be different when we are choosing different random seeds. And also shuffling the data in different ways might also lead to different results. Cherry picking often occurs. By that, what we mean is we try to, we all try to, play around with different parameters like random seed and, different training test split ratios. And we just try to pick the model which gives us the best result. And that is what we mean by cherry picking. And that would often lead to, different results. Hyperparameters to train the models, if they are different, you might, get different results. We also sometimes forget to check overfitting, which might lead to overtraining the models. And so you would wonder, like, if my model was performing really great with the training data, and when I tested it was performing good, but then when I tried to get the performance on an unseen data, it's generalizing poorly, and that might be a result of overtraining your models. On the other hand, we see deeper issues which are under the water and often unseen. Some of those issues are like this. So many a times we also miss checking the distribution of our training and production data. So if the distributions are different, we are going to get different results on our unseen data, which also leads to the fact that the feature which was important for the training data isn't important anymore in the unseen data, leading us to have different results. There might also be some bias in the way we have collected this newly unseen data, which might be like selection bias. The way we have sampled the data leads to different performance. Specific to cybersecurity use case, another reason for reduced performance might be the presence of samples belonging to new malware families, which are originally not a part of the training data set. So when the model hasn't seen any of the malware families introduced in the new unseen data, it cannot generalize well. One of the other points is when the environments where you train the model and get the predictions is different, you're also going to get different results. And sometimes it's also your data, which might have some assumptions or some kind of filtering going on, which might lead to different results. Next slide. So as we are specifically talking about cybersecurity use case here, a small change in performance is a very big deal. And as Laura already explained, getting low false positives is very important. Like we never would like to block Google and be in trouble. So it is better that in our working scenario, it is better that a malicious portable executable file is not detected than blocking a benign portable executable file, given that it would directly affect the user experience. So let's consider an ideal scenario where we have just one or two files and algorithm classifies them as, let's say malicious, and there is a human who is often involved in cybersecurity use cases because this person is an expert and has deeper understanding of how this particular malware behaves. So life is very simple. This person can and analyze these two malware samples and his work is done. But then let's think about a scenario where we have streaming data and we have 20 to 50,000 malicious files where the burden on this person drastically increases. And that's why we would like to point out to the fact that reliable predictions are particularly important in environments that need to scale, and that's how lower performance increases analytic burden. So now we are going to discuss some of the tips we have learned along the years so that we can overcome challenges in reproducibility. So firstly, understanding the data well can really help you to understand the data distribution. A model can generalize well on unseen data when the data is drawn from a similar distribution. And really performing feature selection and looking at features which are not contributing to your model's performance and removing them makes a lot of sense. And also kind of like checking feature importances is really important. One of the things we have considered doing in our experiment in future is training with real world data from our production environment and then checking the performance. Third point we would like to highlight is to not be scared to add new features, which makes sense for your real world data, because every data is different. And so if we try to reproduce something without knowing all these reproducibility issues and how you can overcome challenges will be a problem. Fourth point we would like to highlight is doing a literature review. So when you are doing a literature review, look for features that hold across different studies, because that is a strong indication of relevant and most important features which work for most of the people. Next slide.
Sorry to interrupt, ladies. Just wanted to give you the 5-minute warning here.
Oh yeah, just I'm almost done. So be mindful about the paper you are selecting. So ask yourself all the questions when you are, going through the paper, like, are there assumptions on the data environment? How am I going to train the model? Do I have all the information I need? Can I obtain similar data and results? And making sure that you can reproduce, the original results before you try it on your new data. And then something you could also use is MLflow for tracking all the experiments you do, logging, so that you do not at the end forget which model I used and which gave me the best performance, right? At last, we want to point out that there is no generic classifier which will work for every data set. So there is no free lunch theorem. I think everybody might have heard of. So there is no one solution which might fit for all of your use cases. Next slide. So what we would like you to get out of our slides is, first point, reproducibility is a common problem, and in often cases, you would not obtain the same results. And adjustments are usually necessary to have an algorithm that works on your specific data and environment. So your model may not look the same, but with adjustments, it has definitely improved. Thank you for listening to us. If you have any questions, please ask us or reach out to us. These are our details.
Thank you so much, ladies. We'll move to question and answers now.
Yeah.
We have a couple here. There's one on how do you account for concept drift when designing or training a model?
Okay. Yeah, that's a good question. So I think that first of all, their concept drift is the fact that you have trained on a particular data set, and over time your data distribution is changing, so your model is not able to capture anymore because it was trained on a particular assumption of how the data looked at the time. So I would think as a first step is ensure that you're training on current data, specifically for cybersecurity. It's an environment that is always changing. You have a lot of different threat actors changing their techniques all the time. So you, first of all, want to ensure that you're using current data. And particularly in terms of, I'm not sure, I wouldn't say there is a perfect solution out there. There are people that, besides take into account current data, then over time you evaluate the distribution of your features. Once you deploy it, they see a change and they have to train. I would say that the solution is just you will have to retrain your model over time to ensure that your data is up to date. So I don't think there is a solution that will solve, when you're training your data for this kind of issue.
Yeah, absolutely. And I would like to add that there are few techniques which could be used to make sure. I think it all comes down to data distribution. So when you actually notice distribution in the unseen new data, then you would need to see where that distribution changes, and then how can we start retraining our models and taking into account the new data we have. So yeah.
I have a question. How often do you check in cybersecurity for data drift? Is that like a daily thing, a weekly thing? Does it vary?
I think it definitely varies, because also threat actors keep changing their tricks. So we have, maybe let's say a window of 3 to 6 months where we go back and check, how the data varies now. Do you want to add anything, Laura?
Yeah. So yeah, exactly. I don't think there is a particular threshold. I think it really depends. There are certain use cases that certain features are known to hold over time, but there are other particular use cases that the threat actors are changing and will most likely change over time. So it really depends on your use case and and the type of things that you're detecting and that your algorithm is trying to detect.
Okay, we have 5 seconds. So thank you, ladies, for being here. Thanks, everyone. See you in the next sessions.
Thank you. We appreciate your attendance. Yeah, thank you.
Thank you for listening to us. Yeah.
Okay. Wow, that got close at the end. Are you guys able to share your slides? Because I can put them with the recording when we post that later, if you guys are able to do that.
Yep, I have the PDF downloaded. I think they sent in the speakers channel. I can just send there.
Oh, that'd be perfect.
Yeah, I saw that someone asked.
Cool. Yeah, we're going to collect all those, and then we will put it in the YouTube channel, and then there's also an accompanying blog post and data circles that will be about your talk with your bios and the abstract of the thing, and we'll put the slide link in there too, besides the YouTube. So that was a really great talk. Super interesting.
Thank you. Yeah, we're looking forward to attend the other ones and see the recording.
Cool.
Okay, I guess we can leave, right?
Yeah, so you guys are good to go. I just have to let it run for a minute.
Okay, bye.
Bye-bye.
Thank you so much.